So let me continue. We have started with the concept of cointegration as developed in Granger in a paper 1981. We have defined cointegration in this way: two or more time series variables, integrated variables, showing আমি একটু পরে রিং ব্যাক করছি, ব্যস্ত। So if two or more time series variables, non-stationary time series variables, showing similar kind of stochastic trend, they will be co-integrated. Question is, why do we need this kind of concept of co-integration? To understand the use of co-integration, we have discussed the possibility of spurious regression as may appear in the case of a time series model. Spurious regression means in a simple linear regression model or multiple linear regression model, you may get highly significant results in statistical sense, but in reality, there is no meaning at all of this result. So this kind of problem may appear if we use time series data in a linear regression model. Okay. And why this kind of problem appears? This kind of problem will appear simply because the error term incorporated in a linear regression model is not white noise at all. Although we assume the random term to be white noise, but because of the basic properties of the time series variables, ultimately in the model, the error term may not be white noise and the problem of spuriousness may appear. Now, how do we identify whether our model is spurious or not? We can identify by looking at two or three statistics. One is the t statistics, another one is r squared, another one is Darwin-Watson. If you have highly significant t statistics, high value of r squared, but simultaneously if you have low value of Darwin-Watson, it may be an indication that your result may be spurious, and in that case we have to be careful. And this spuriousness appears because the random error involved in our model is not white noise. Why? To understand this statement, we try to understand the meaning of white noise epsilon. White noise epsilon is white noise, implies the deviation of the actual situation from the theoretical one are temporary phenomena. So if the deviation of the actual situation from the theoretical one is purely a temporary phenomenon, in that case your model will be meaningful, otherwise not. So your linear regression model will be meaningful only when epsilon t is white noise. So we have to concentrate on the behavior of epsilon t to understand whether our model is meaningful or not. Okay. If we have a cross-section data, by default the error term will be white noise or the random error. But we have a time series data, particularly if we have a non-stationary time series data. In that case, there is no guarantee that the random term will be white noise, although we assume that random term is white noise initially. Okay. Why? We will next come to this point, why epsilon t may not be white noise in the model, although we assume initially epsilon t is white noise. In other words, the assumption of random behavior of epsilon t may not be valid in the case of a time series data. Okay. So what we have to do, we have to look at the behavior of epsilon t. to understand whether you have a meaningful model or not. Now the question is, how do we analyze the behavior of epsilon t? Because epsilon t by definition is unobserved. We cannot observe epsilon t. So epsilon t is unobserved. So how do we examine the behavior of epsilon t, that is whether epsilon t is white noise or not? Okay, so to have a meaningful model, we need epsilon to be white noise. Now the question is how to identify whether epsilon t is white noise or not. If you have information on epsilon t, you can carry out some statistical tests to find out whether epsilon t is white noise or epsilon t is stationary or epsilon t is non-stationary, etc. But epsilon t by definition is unobserved. We cannot observe epsilon t. So how to examine the behavior of it? So we have to follow the indirect way. How to follow it? Let we define epsilon t in terms of this model. By simple manipulation, we can have epsilon t is equal to this: x1t minus beta 1 minus beta 2 x2t. Just from equation 1, if we take epsilon t in the left hand side and all other variables in the right hand side, you have got this kind of result. So what is the meaning of this? Epsilon t, the error which is unobserved in reality, this error could be looked at as in this form. We have a data on x1, we have a data on x2. So as x1 and x2 are observed, we can look at epsilon t in terms of x1 and x2. How to look at the behavior of x1t? If you look at closely the structure of the right hand side, we can define the right hand side as the linear combination of x1t and x2t. Okay, how to get epsilon t? Epsilon t is equal to x1t minus beta 1 minus beta 2 x2t. In other words, epsilon t could be looked at as a linear combination of the variables involved in your regression model. Okay, so for meaningful model, we need epsilon t to be white noise. So we can say it in another terms. For meaningful model, we need the linear combination of the variables is to be white noise. Have you got my point at this stage? This linear regression model will not be spurious. This linear regression model will be meaningful only when epsilon t is white noise. Why? Because if epsilon t is white noise, the deviation of the actual situation from the theoretical one will be a purely temporary phenomenon. And in that case, we can use this model to explain the theoretical proposition we have. For that reason, for meaningful model, we need epsilon to be white noise. But epsilon is unobserved. So how to understand epsilon to be white noise or epsilon to be non-stationary? For that purpose, we define epsilon t in this way. Epsilon t is equal to x1t minus beta 1 minus beta 2 x2t. In other words, at this stage, we can say epsilon t, the error, can be looked at as the linear combination of the time series variables x1t and x2t. Okay. Now, epsilon t to be white noise when the linear combination of x1t and x2t will be white noise. When the linear combination of x1t and x2t are white noise, in that case, epsilon t will be white noise or stationary, and OLS provides you a consistent estimates. And in that case, there will be no possibility for spurious result. So for meaningful estimation, we need random error to be white noise. In other words, for meaningful results, we need the linear combination of the variables used in a linear regression model is to be white noise. when the linear combination of the variables is white noise, then the variables are said to be co-integrated. In other words, try to look at this relation. When epsilon t will be white noise, we assume beforehand x1t is non-stationary, x2t is non-stationary. Suppose we are considering non-stationary with unit root. Okay, and suppose x1t contains one unit root, x2t also contains one unit root. So if the number of unit roots involved in different time series are the same, in that case we can expect the nature of the stochastic trend involved in the series may be similar, roughly similar. But if the number of unit roots are different, suppose x1t contains one unit root, x2t contains two unit roots, for example. In that case, the stochastic trend in x1t and stochastic trend in x2t will obviously be different because the number of unit roots are different in these two series. But if the number of unit roots in x1t and number of unit roots in x2t is the same, in that case we expect stochastic trend involved in x1, stochastic trend involved in x2 may be similar. So if x1t and x2t follows similar kind of stochastic trend, in that case in epsilon t the trending behavior will be eliminated. Just consider it purely technically. x1t has a stochastic trend, x2t has similar kind of stochastic trend. So if we take minus or if we deviate one stochastic trend from another stochastic trend will be eliminated and there will be no stochastic trend in epsilon t. So in that sense, epsilon t will be stationary if the stochastic trend in x1t and stochastic trend in x2t is similar. Have you got my point? So if the stochastic trend in x1t and stochastic trend in x2t are similar, in that case we may get the error term as a white noise or purely random, and our regression result will be meaningful. Our regression result will not provide spurious estimation. So for meaningful estimation, we need the variables involved in the model should follow similar kind of stochastic trend. Again, at the beginning, we define if the non-stationary variables follow similar kind of stochastic trend, they will be co-integrated. Therefore, we can say the variables will be co-integrated when their linear combination will be white noise or their linear combination will be stationary. So we can define co-integration in alternative way. Initially, the variables are non-stationary with unit root. We are considering for simplicity two variables x1t and x2t. So suppose initially x1t non-stationary with single unit root, x2t non-stationary with single unit root, but their linear combination, that is x1t minus beta 1 minus beta 2 x2t, this linear combination is stationary. In that case, x1t and x2t will be called co-integrated. Is it clear?
Yes, sir.
So if the variables contain single unit root, we are focusing on single unit root in x1, single unit root in x2. If x1 has single unit root, x2 has multiple unit root, you will not get the possibility of co-integration, because in that case, the nature of stochastic trend in x1 and the nature of stochastic trend in x2 will obviously be different. So if the nature of stochastic trend involved in different series are different, the different series will not be co-integrated, because the definition of co-integration, co-movement of the integrated series, that is the stochastic trend of one series will follow the stochastic trend of the another series. In other words, the nature of the stochastic trend of different series should be similar for co-integration. So if the stochastic trend are different, so there will be no possibility for co-integration. So if x1t contains 1 unit root, x2t contains 2 or 3 unit roots, for example, in that case, x1t and x2t will not be co-integrated, and in this case, epsilon t will not be white noise. Why? In that case, you cannot eliminate the trending behavior, because take it purely technical. Suppose x2t contains 2 unit roots, implying that the strength of the stochastic movement of the x2 will be significantly higher than the strength of the stochastic movement of x1, because x1 contains 1 unit root, x2 contains 2 unit root. So the strength of the stochastic trend in x2 is greater than the strength of the stochastic trend in x1, and we cannot eliminate the trending behavior by looking at the linear combination like this. So we can eliminate the trending behavior only when the nature of the stochastic trend involved in different series are similar. So in that case, we have the possibility of purely random error turn, and the variables will be co-integrated. So if we sum up the basic points here, if we have a time series data and we want to estimate the relationship between them by applying OLS or maximum likelihood, whatever may be, if the variables are non-stationary, we cannot apply OLS without considering the stochastic behavior of the series, because in that case there is a possibility of getting spurious regression. So what we have to do in that case, we have to examine whether the variables we have are co-integrated or not. If the variables are co-integrated, in that case the error turn will be random and we will get the meaningful relationship between the variables. For that reason, co-integration is necessary for having a meaningful estimation with non-stationary time series data. Okay. So we can define co-integration formally in this way. If x1t and x2t in a two regression model are integrated of order 1, that is I1, integrated of order 1 means both the variables contain a single unit root. So if x1t and x2t are integrated of order 1 and their linear combination is stationary, in that case x1t and x2t will be co-integrated. And co-integration actually provides you the long run equilibrium relation. Why long run equilibrium relation? Take again the structure of equation 1. This equation will be an equilibrium equation only when epsilon t equal to 0. We define the implication of epsilon t, the presence of epsilon t in a regression model, as the deviation of the actual situation from the theoretical one. And this theoretical one could be equivalent to the equilibrium, because theory always implies some kind of equilibrium. If we consider any kind of theory we have in economics, in every theory deals with equilibrium. So theoretical relationship will always be in equilibrium. So if epsilon t is stationary, if epsilon t is white noise, or x1t and x2t are co-integrated, in that case, after taking the mean value, this becomes 0 and you have a linear relationship. This linear relationship will provide you the equilibrium relationship. And this equilibrium is long run. Why long run? Because we are considering a time series variable. For a time series variable, we are considering a longer span of time. So in that sense, the estimated relationships in any regression model with time series data provide you a long run relationship. Similarly, if we have a regression model with cross-section data captures a very short period of time. For that reason, the estimation of the regression model with cross-section data provides you a short run equilibrium, but the estimation model with time series data provides you the long run equilibrium. So alternatively, we can say if the variables provides you the long run equilibrium, in that case the variables will be co-integrated. So this is the basic definition of co-integration as used in Granger 1981. Later on, this definition has been extended for more variables, and we can complicate this definition a little bit, but at this stage we avoid this complication. The complicated definition of co-integration, the extended part of co-integration will be discussed in semester 3 if you have advanced econometrics as a choice for optional paper. So we retain those parts for the advanced econometrics. So for you, for second sem, for the general discussion on time series econometrics, it is sufficient to have some conceptual issues relating to co-integration. What is meaning by co-integration? How do we need co-integration for a meaningful estimation like this? Okay. Now the next part we have to deal with how to test for co-integration. There are so many tests, but as for general discussions, we consider here only a very simple test known as Engle-Granger two-step method. Engle-Granger two-step method. So how to test for co-integration? If we follow this method is called two-step. Two-step in that sense, in step 1, we have to estimate, suppose we are concentrating this relation. We want to estimate this relation. And what we want to test whether x1t and x2t are co-integrated or not used in this model. So for that purpose, according to Engle-Granger two-step methodology, in stage 1, we have to estimate this model by applying OLS. Okay. And in stage 2, after estimating this model, we can find out the residual. Error by definition is unobserved, but residual is observed because residual is the estimated part. So after estimating this model, we can find out the residual. And after getting the residual, what we have to do? We have to examine the behavior of the residual. If the residual is stationary, then your model will be meaningful, and in that case the variables will be co-integration. So in the second stage, if we find that the residual is stationary, then we can say that the variables involved in a model will be co-integrated. In that way, we can test co-integration by following Engle-Granger two-step method. So let me explain this method in a very simple way. So already I have mentioned it involves 2 steps. In step 1, we estimate the model. In step 2, we have to carry out unit truth test of the residual obtained from the estimated model. And if the null hypothesis is rejected, in that case, we can say that the variables will be co-integrated. Okay. Now, before carrying out these 2 steps, beforehand, you need to examine the nature of non-stationarity of x1t and x2t separately. Why? Because the possibility of co-integration appears only when the stochastic behavior or the stochastic trend involved in x1 and the stochastic trend involved in x2 are similar. If they are dissimilar, there is no question for co-integration. So for that reason, before carrying out co-integration test, we have to test for unit root individually the variables we are trying to use in our model. So if we use x1t and x2t in estimating this regression model, so in first of all, we have to find out the order of integration of x1t and x2t by applying augmented Dickey-Fuller. We have discussed in the last class how to carry out augmented Dickey-Fuller test to find out the presence of unit root in a series. Okay, so by applying augmented Dickey-Fuller, we can first find out whether x1t and x2t contains similar number of unit roots. That is, if x1t has one unit root, x2t also should have one unit root. If x1 has two unit roots, for cointegration, x2t should also have two unit roots. So beforehand, before entering into the two-step method, we have to look at whether the variables or whether the series we have are integrated of same order or not by applying the augmented Dickey-Fuller test. So this is the step, this is the necessary step involved in carrying out this test. Now at this stage, if we understand, or if we have the number of unit roots in x1 and number of unit roots in x2 are similar, in that case we follow step 1 and step 2. So if x1t and x2t are non-stationary but they contain same number of unit roots, then we estimate the linear regression model. After estimating the linear regression model, we have to find out the residual, and in the second step we have to carry out the unit root test for the residual. Okay, that is, we have to test whether the least square residuals epsilon hat t appears to be I naught or not. I naught means integrated of order 0. Integrated of order 0 implies the series will be stationary. So to carry out unit root test for the epsilon hat t by following Dickey-Fuller, we can use this model, and this is the basic hypothesis we have to carry out. H naught rho equal to 0, rho less than 0, rho equal to 0 indicates the presence of unit root in epsilon hat t. So if H naught is rejected, in that case epsilon hat t will be stationary. If epsilon hat t is stationary, in that case we can say x1t and x2t are co-integrated. If x1t and x2t are co-integrated, the estimated model by applying OLS provides you the meaningful result. So this is the gist of the discussion for today's class. Okay, now if the epsilon t, a new series you have got after estimating the model, the residual, and the residual may follow AR1, may follow AR2 or AR3, whatever may be. So if epsilon t follow AR1, the appropriate model for testing unit roots looks like this. But if epsilon t follows higher order autoregression, we need to consider the augmented Dickey-Fuller kind of model as we have discussed yesterday's class for any time series variable with higher order autoregression, how to carry out the Dickey-Fuller test. So here we also have to follow the similar process. So in this way we can carry out co-integration test. But this co-integration test has some inherent problem, and we have to eliminate this problem by following or by extending the model further, by considering the system of equations, by considering the further development of the methods, by considering the extended concept of the co-integration, etc. That will be for the advanced econometrics. So time series econometrics is end today up to the concept of co-integration till now. Okay, so we have 5 minutes left. So if you have any questions, you can ask me and I shall try to clear those parts which is not cleared till now.
Excuse me, sir.
Yeah.
Sir, বললাম যে আপনি একটু ওই null hypothesis এর পার্টটা রিপিট করতে পারবেন?
Null hypothesis আমরা এই গত দিনের ক্লাসে তুমি ছিলে? গতদিনের ক্লাসে আমরা যেভাবে নাল হাইপোথিসিস ধরেছিলাম এটাও ঠিক তাই। এটা যেহেতু আমার ফার্স্ট ডিফারেন্স ফর্মটা হচ্ছে লেফট হ্যান্ড সাইড ভেরিয়েবল, এই জন্য রো ইকুয়াল টু 0 উইল ইন্ডিকেট দ্য কোএফিসিয়েন্ট ফর air 1 component, that is phi 1 equal to 1, and rho means rho is equal to phi 1 minus 1. For that reason, rho equal to 0 indicates phi 1 equal to 1. So the non-rejection of H naught indicates the presence of unit root in the series, and rejection of H naught means the series has no unit root, that is the series you have is stationary. Okay, and I have got one question in my mail. Somebody asked me I have mentioned some problem in Dickey-Fuller test. Why in Dickey-Fuller test we cannot use the conventional t statistics? Because we have shown by following simple steps that the mean value of the statistics phi 1 hat equal to 0 by phi 1 hat, mean value for phi 1 hat is equal to 1 by the null hypothesis, and the variance of the phi 1 hat equal to 0. Okay, we have derived the variance of phi 1 hat, and under null hypothesis the value of the variance of the phi 1 hat equal to 0. So you have a distribution of phi 1 hat with mean value equal to 1, variance equal to 0. So what is the interpretation of this result? If you have a distribution with variance equal to 0, this distribution has no use at all for practical sense, because what is the meaning of zero variance? Zero variance implies that all values of the variable is the same. So if you have a series y, so all values of y are the same, whatever may be your time point. So if all values of y are the same, you have a if this kind of distribution cannot be used for further analysis, for statistical analysis. So for statistical analysis, we need some kind of variation in the data. We need some kind of variation in the variable that is captured by the variance. So for meaningful distribution, we need some non-zero variance, that is positive variance. Whatever may be the mean value of it, we need some positive variance. But by default, in the Dickey-Fuller statistics, phi 1 hat, the variance is 0 and the mean value is 1. So as variance is 0, we cannot use this distribution for testing of hypothesis or for the purpose of statistical inference. This is the basic problem in Dickey-Fuller test. For that reason, we cannot apply the normal distribution or t distribution in carrying out Dickey-Fuller test, and we need a special kind of distribution, and by applying some simulation we can find out similar kind of distribution that could be applied for Dickey-Fuller test. Okay, and the nature of this similar kind of distribution will be discussed in the advanced econometric class, not here, because it is somehow complicated and it may be difficult to understand at this stage. So you should just keep in mind the basic problem in the Dickey-Fuller test. The basic problem is the variance is 0, which has little meaning in reality to use the distribution of this variable. For that reason, we need to search for the another variable that could be used for statistical inference. Okay, so any question? We have 2 minutes. Any question from your point? Please be louder. Yes. তোমার কথা আমি বুঝতে পারছি না, কেটে কেটে যাচ্ছে, একটু ভালো করে বলো। But we have a less than a minute time. We have a less than a minute, it shows. So I have a very little time. So if somebody have any questions, you can ask clearly, or I shall provide you the handout. I shall provide you the recorded version of this class. So you can repeat it at home. And those who cannot join this class, you can share for them. And the next class will be on Monday, and next class will be on the panel data econometrics. So we can take care of panel data on Monday at the same time 11:30. It is okay for you?
Yes, sir.
Okay.
Yes, sir.
Okay,
We
sir.
will meet next Monday at 11:30 for basics of panel data. We cannot proceed more because uh, Zoom is not perfectly substitute for live class discussion. So for that reason, as possible, I shall try to provide you some basic concepts of panel data, the basic advantages of panel data, some basic models of panel data that could be used in econometric model. Okay, so we'll again meet on Monday at 11:30.
Mas sei para onde